So last time we talked about end behavior. This time let's talk x-intercepts. So we'll start with an example function, f of x equals x cubed minus 4x. So in order to find the x-intercepts, we want to look at where y is equal to 0. So we'll go find the x-intercepts, which means y equals 0. So if we go back and say, this is going to be the y, we'll make that 0. We'll say 0 equals x cubed minus 4x. And when we have equations equal to 0, if we can factor, that puts us in a good position. So we recognize there's an x in common. We factor out the x. Then this is a difference of squares. So that becomes x plus 2, x minus 2. And now that we factored it down, 0 equals number times number times number, which means our options are the first number is 0, or this number is 0, which means x is negative 2, or this number is 0, which means x is positive 2. We go back to our graph and we're going to mark. X can be 0, x can be negative 2, x can be positive 2. Those are the x-intercepts. And now to get some more information about the shape of the graph, I'm going to make a table. I'm going to plug in values on either side of negative 2. So I'll plug in negative 3 and negative 1. And I'll put in values on either side of 2. So I'll put in 1 and 3. If I plug in negative 3 into here, that's negative 27. Minus 4 times negative 3 gives me plus 12. That's negative 15. If I put in negative 1 cubed is negative 1. Then negative 4 times negative 1 is plus 4. That gets me 3. I'll put in regular 1 cubed. Then minus 4 times 1 is minus 4. That gets me negative 3. Then I'll put 3 cubed, 27. And then minus 4 times 3 is minus 12. That's a positive 15. So if I mark those points on the graph, negative 3 comma negative 15 way down here, negative 1 comma positive 3, then 1 comma negative 3, and then 3 comma positive 15 way up here. If I connect these, the shape is going to look something like this. All right, so we notice there are 1, 2, 3 x-intercepts, and there are 1, 2 turning points, which means we were going up, we turned around and came down. We were going down, turned around and came up. Now, without actually proving this or fully motivating this, I'm going to make a bold claim. I'm going to say if the degree, so in this case, the degree of the polynomial is 3, I can say up to this number, up to 3 x-intercepts. I'm going to say up to 1 fewer than the degree, up to 2 turning points. This is going to be a thing we can say about polynomial functions. Let's conclude this example and then look at another one. So this time, let's go with g of x equals x to the 4th minus x cubed minus 2x squared. So we'll start by trying to find the x-intercepts, which means that y is going to equal 0. So we'll take, once again, y equals 0. Say 0 is equal to x to the 4th minus x cubed minus 2x squared. And we're going to try to factor this. So we see there's an x squared in every term. We'll start with that. This becomes x squared. This becomes minus x. This becomes minus 2. And we look at this and realize that's a quadratic that we can factor nicely, looking for numbers that add up to negative 1 and then multiply to negative 2. So negative 2 and positive 1 will fit that description. And finally, we have number times number times number equals 0, which means this is equal to 0, or this whole thing equals 0, which means x is 2, or this whole thing is equal to 0, which means x is negative 1. So on our graph, x could be 0, or x could be 2, or x could be negative 1. And then we'll make a table. And we'll say a number to the left of -1, a number between -1 and 0, a number between 0 and 2, and then a number to the right of 2. So we can take these values of x and plug them in up here, or maybe we can do something a little bit different this time. We can say this right here was g of x, and as we factored, we were only ever writing down something that was equivalent to the previous step, which means this is exactly the same as our original, and we can write g of x is equal to x squared times x minus 2 times x plus 1. Which means we can take this -2 and plug it in there, and there. So -2 squared is 4, -2 minus 2 is -4, and then -2 plus 1 is -1. Put it all together, we get positive 16. Then -1/2 in for x, so -1/2 squared is 1/4. Then -1/2 here, minus 2, gets me -5/2. And then -1/2 plus 1 gets me 1/2. Multiply all the tops, I get -5. Multiply all the bottoms, I get 16. And there we have it. Now I'll plug in 1. So 1 squared is 1. Then 1 minus 2, -1. 1 plus 1 is 2, for a grand total of -2. And then finally plug in the 3. 3 squared is 9. 3 minus 2 is 1. And then 3 plus 1 is 4. We get 36. Okay? So when we sketch this, I'm going to try to exaggerate the features in here. So I'm going to say 16 is way high up in the sky. And then -1/2 comma -5/16, somewhere around here. And then 1 comma -2, so that's going to be farther down than -5/16. And then 3 comma something way high in the sky. So if I sketch, it'll look something like this, where I come down, and then I come back up. And then here, I'm going to do something kind of interesting. I come down, and then I do this. So here and here, at these x-intercepts, we're coming through the x-axis. But here, we're doing what's called a touch and turn, where you don't actually go through the x-axis, but you turn around there. And it turns out, I'm going to ruin the surprise now without actually proving or motivating it, the distinction between this kind of x-intercept versus this kind of x-intercept is the power that shows up on the factors. So notice here the power is 1 and the power is 1. These two correspond to x-intercepts, where you go through the x-axis, and here, this 2 corresponds to a place where you touch and turn at the x-axis. Now the final thing I want to comment in this example is the degree of this polynomial is 4. And we said last time, without proving or really motivating, that the number of x-intercepts can be up to the degree. So I can have up to 4 x-intercepts. In this case, I have 3 different x-intercepts, but up to 4. And finally, I can have up to 4 minus 1, which is 3 turning points. And in this case, I have 1, 2, 3 turning points. I should be careful. When I did this, I don't want you to believe that -1/2 and 1 are necessarily the turning points. The turning points will occur somewhere in this area, but I have not demonstrated to you that these are the specific turning points. That will be a topic in the future. All right, let's lay this example to rest, and we'll do one more. Now let's try h of x equals x to the 5th power plus 4x to the 4th power plus 4x to the 3rd power. Let's find the x-intercepts, which means y equals 0. So we'll say 0 equals and again, we'll try to factor. This time we have an x cubed in all the terms. So we'll factor this out. X squared from here, then plus 4x from there, and then plus 4 for the last term. And that's a quadratic that we can factor by looking for numbers that add up to 4 and multiply to 4. So I have positive 2 and positive 2. And in fact, these are the same as each other. So I can write this as 0 equals x cubed times x plus 2 squared, like this. And we know that x could equal 0, or this could equal 0, meaning x is negative 2. So we would mark 0 and negative 2. Then let's go and make a table. I'm going to pick something to the left of negative 2. I'm going to pick something between negative 2 and 0. I'm going to pick something bigger than 0. And I'm going to plug these not into there, but I'm going to look back here and say, well, this was h of x. And from here down, I was only factoring. So this is completely equivalent to that, which means I can write h of x equals x cubed times x plus 2 in parentheses squared. So if I plug in negative 3 into there, negative 3 cubed is negative 27. And then negative 3 plus 2 is negative 1. Square it gets me 1. So overall, that's negative 27. Then negative 1 into x, negative 1 cubed is negative 1. Negative 1 plus 2 is positive 1. Square it is still 1. All over, that's negative 1. So 1 go into x. That's 1 cubed is 1. Then 1 plus 2 is 3. Then square that gives me 9. So I have this. So if I go to sketch, negative 3 comma very negative down here, and then negative 1 comma negative 1, and then 1 comma 9 up here somewhere. I've exaggerated this a little bit again. So if I graph this, so I'm cheating because I know what this looks like. It turns out it looks something like this. So here we observe this is that touch and turn we were talking about last time. But here we have something brand new. Instead of going right through like we did in the first example and part of the second example, this time we flatten out but then go through. And it turns out this behavior, like I hinted before, is based on these powers over here. So last time I said if the power is 2 or even, I'm going to get some kind of touch and turn behavior. And this time, instead of a power of 1, we have a power of 3. And evidently that causes this flatten out and then go through behavior. So then, I guess we'll also talk about this degree and what that means for the rest of the things. So the degree of this polynomial is 5. And that means I can have up to 5 x-intercepts. And in this case, I have 2, but 2 is up to 5. And then finally, I can say up to 5 minus 1 is going to be 4 turning points. And the turning points, there's a turning point here. There's a turning point somewhere in here, maybe not exactly at negative 1. There's another turning point. And then this, we don't call that a turning point because it doesn't actually change directions. It's increasing, and then it flattens out, but it keeps increasing. So in this case, I have 2 turning points, which is up to 4. Okay, let's try to summarize what we just saw. So in all of that, our goal was to find x-intercepts. And in order to do that, we need to make y equal to 0, which prompted us to factor things. So if we look at our original function f of x, this started off as x cubed minus 4x. And we took this and factored it, so we ended up with x times x plus 2 times x minus 2. And this, and this are what we call the factors of f of x. So if I write the factors, I can list them as x, x plus 2, and x minus 2. And those three are the factors of f of x. Then we said, in order to find the x-intercepts, we want to make the y 0. So we'd set this equal to 0. Then we'd say, in order to make this 0, I can have either x is equal to 0, or I can have x is negative 2 to make this whole thing 0, or I can have x equals 2 to make this whole thing 0. Now these numbers, these are called the zeros of the function f of x. Because if I take any of these and plug it into f of x, I should get 0 as a result. So we're going to write the zeros are x equals 0, x equals -2, and x equals +2, corresponding to each of their factors. The zeros and the factors are intimately related like this. Now the third idea is going to be based on the exponents on each of these factors, which I asserted was going to be important in understanding the graphs. The word is multiplicity. So the multiplicity of each 0 is going to refer to the exponent on the corresponding factor for that 0. So in this case, the factor has an exponent of 1, which means the multiplicity of the 0 is 1. This factor has an exponent of 1, which means the 0 corresponding to that factor has a multiplicity of 1. And then this last factor has an exponent of 1, so the multiplicity corresponding to that 0 is 1. And when we made the graph of this, we said there is a 0 at x equals 0, there's another 0 at x equals -2, and there's another 0 at x equals 2. And then each of these has a multiplicity of 1. So it turns out in each case, I'm going to go through the x-axis, cross right through it. Let's bring back the end behavior business. So we're going to say, as x approaches infinity, and as x approaches -infinity. Remember, this is a degree of 3, which is odd, and the leading coefficient is 1. So I'm going to write down degree is 3, and leading coefficient is 1, and that's positive. So we said if it's an odd degree and the leading coefficient is positive, put in a big positive number, I get a positive result. So f of x goes to +infinity. I put in a very negative number, cube it, I get a negative number. F of x goes to -infinity. So my end behavior, I'm going to be going up this way and down this way. So I can say if I start down here, but then cross the x-axis, then cross the x-axis here, then cross the x-axis and end up over there, I can make a sketch of my graph that looks like this, off of the zeros, the multiplicity, and the end behavior. And this is how we're going to try to approach graphs from here on for a while. Let's do the same thing with g of x. So we started with g of x equals x to the 4th minus x cubed minus 2x squared. And we factored this to make x squared times x minus 2 times x plus 1. So those three things are the factors. We have x minus 2, and we have x plus 1. And corresponding to those factors, if I set this equal to 0, I can get the zeros of g of x by saying either that is 0, or that is 0, or that is 0. So my zeros corresponding to my factors are going to be 0, 2, and -1. Now hopefully you see the pattern, right? Because this is the number that makes that specific factor 0. This is the number that makes that specific factor 0, and so on. Then for the multiplicity, we inspect the powers. So the powers on the factors are 2, 1, and 1, so the corresponding zeros have multiplicities of 2, 1, and 1. And then we can talk end behavior, because we can look at the degree and say, okay, the degree is 4, it is even. The leading coefficient is 1. And so we can say, as x goes to infinity, big positive number to the 4th power is big positive number. So f of x goes to infinity. Then as x goes to -infinity, very negative number to an even power turns big positive. So f of x goes to +infinity. Now we can turn around and sketch a graph using this info. So we know that the zeros are 0, 2, and -1. They're all real. They correspond to x-intercepts. 0, 2, and negative 1. And we know the end behavior is it's going to go up over there, and it's going to go up over here. So we can then say this 0 has a multiplicity of 1. That means it's going to go right through the x-axis. This 0 has a multiplicity of 2, and that meant it was going to touch and turn. So it's going to not go through, it's going to touch and turn around. And then at x equals 2, I have a multiplicity of 1, so I'm going to come through the x-axis, and in order to do that, I have to turn around somewhere, and I'm going to go up to match my end behavior. And that's the sketch of my function using that method. Now let's do h of x. So h of x was x to the 5th power plus 4x to the 4th power plus 4x cubed. And the way we factored this was we had x cubed multiplied by x plus 2 squared. So the factors x and x plus 2. And their corresponding zeros, if I set this equal to 0, we said either x is equal to 0, or to make this 0, x is negative 2. So the zeros of h are 0 corresponding to this and negative 2 corresponding to this. To get the multiplicities, we look at the exponents 3 and 2. So this 0 has a multiplicity of 3, this 0 has a multiplicity of 2. Then we can look at end behavior. We can say the degree is 5. That's an odd degree. The leading coefficient is the number in front of the x to the 5 term. That's 1. And then our end behavior, as x approaches positive infinity, big positive number to the 5th power is big positive. F of x approaches positive infinity. And then as x goes to negative infinity, negative number to an odd power is negative, so I'm going to get f of x is very negative. You can sketch a graph. So I know my end behavior, as x goes to the right, y goes up, and as x goes to the left, y goes down. So I'm coming from here, I'm ending up there. I know my zeros are both real, they both make x-intercepts. And the multiplicity here is 3. The multiplicity here is 2. So I'm going to come from here using my end behavior. And then I'm going to touch and turn at x equals negative 2. Then, because I have a multiplicity of 3, I'm going to cross, but in a special way. I'm going to flatten out and then go through. And so I have to turn around here. So I flatten out, go through, and then I continue on to my end behavior. And there, I have a sketch of h of x. Let's do a fresh example that includes a lot of the different elements we've been discussing. Here's our function. And what we want to do is sketch a graph using the end behavior and the x-intercepts. Okay, so let's start by trying to find the end behavior, which means we should identify the leading term. We see the biggest power of x shows up right here, so the degree is 4. And the leading coefficient is the negative 4 attached to the x to the 4th power term. So the end behavior becomes, as x goes to positive infinity and x goes to negative infinity. So if we put a big positive number here, positive to the 4th power is positive, multiplied by negative gets us a negative number. F of x goes very negative. Then if I make x a negative number to the 4th power is positive, times the negative coefficient is going to be negative. Okay, so there's my end behavior. Then to get the x-intercepts, let's try to factor this down. So we'll go f of x is equal to, and let's go ahead and put it with the leading term first. Like this. And we recognize there's an x squared in each of these terms. We want to factor that out. And I have a personal preference for pulling the negative out of the leading term with it. So we'll have something like this. Excuse me, negative here. And then we want to factor the quadratic that's inside here. And I'm going to cheat here, and I'm just going to put down the result. It becomes 2x minus 5 and 2x plus 1. I'm not going to go over how I got that. I'm just going to assume that you already know how to factor. But from here, I know the factors are x, 2x minus 5, and 2x plus 1, which means the zeros are going to become x equals 0. To make this 0, I need x equals 5 halves. And to make this 0, I need to make x negative 1 half. And the multiplicity, I'm going to have this with a multiplicity of 2 because that factor has an exponent of 2. These factors both have exponents of 1, so the zeros have multiplicity 1 and 1. Okay, so now to finish off the discussion, we are going to graph the function. So we know the end behavior. I'm going to have y is going to be going to negative infinity on either side, so I'll have this down here. And I have 3 real zeros, so I have 3 x-intercepts at 0, at negative 1 half, and at positive 5 halves. And I know coming from here, my 0 of negative 1 half has a multiplicity of 1. So I'm going to go through the x-axis. My 0 at x equals 0 has a multiplicity of 2, so I'm going to turn around, but then I'm going to touch and turn. I'm not going to go through the x-axis. Then, when x is equal to 5 halves, my multiplicity is 1, so I'm going to come through the x-axis. And I can finish out the sketch by doing this and following my end behavior. And now I can erase this and this. And that is the sketch of the graph of f of x.